Hello, and welcome to today's virtual Commonwealth Club program. My name is Kara Platoni. I'm the Senior Editor for Science at Wired.com, and I'm your moderator for today. Before we get started, we wanted to thank and welcome any Wonderfest members who are joining us today. It is my pleasure to introduce Dr. Michio Kaku. He's a professor of theoretical physics at the City College of New York, and he's the author of The God Equation, The Quest for the Theory of Everything, which has just become a New York Times and Amazon bestseller. Dr. Kaku is the co-founder of string field theory, and he continues Einstein's search for a theory of everything to unite the four fundamental forces of the universe under one unified theory. He's a science correspondent for CBS This Morning, host of popular radio programs Science Fantastic and Exploration, and the host of several TV shows for the BBC and for the Discovery Channel. Just a reminder to all of our viewers that if you have questions for Dr. Kaku, you can please submit those in the chat, and then we'll be getting to those later in the program. So Dr. Kaku, welcome.
Well, glad to be on after hearing such a great introduction. I can't wait to hear the speaker myself.
Well, it all has the virtue of being true. First, I should ask you to explain where you're beaming in today from. It looks like you're in outer space.
No, I'm right here in Manhattan, but behind me, there's a black hole at the center of the Andromeda Galaxy.
Excellent. I hope we get a chance to talk a little bit about black holes in our chat today. But first, I wanted to kind of introduce people to the big idea of your book, people who haven't had a chance to read it yet. So, and now I'm not a physicist. I am a science editor and reporter and lover of science. But if I get anything wrong, you stop me, right? Or tell me if I'm getting hot or cold. So the theory of everything is a quest to unite the two big frameworks that we have for understanding the universe. There's general relativity, which describes gravity and space-time, and there's quantum mechanics, which describes everything else, electromagnetism, strong and weak nuclear force. And so the first describes the biggest things in the universe, and the second describes the smallest things in the universe. And your quest is to unite them all under one umbrella. So I want to know, why do you think that? Why do you think there can be one theory that describes everything?
Well, you know, all of biology can be summarized in the language of chemistry. All of chemistry can be summarized in the language of physics. And all of physics can be summarized by these two great theories that don't talk to each other. They're hostile theories. They have different mathematics, different physical pictures, and they don't combine. So why should God have a left hand and a right hand that don't talk to each other? You know, it's amazing that the great theme of science for the last 2,000 years has been unification. Isaac Newton unified the laws of heaven with the laws of the earth. Maxwell and Faraday united the laws of electricity with those of magnetism. Einstein, with E equals mc squared, unified matter with energy. That's the theme of the universe. So why should this grand theme of unification be spoiled at the most fundamental level? The level at which we have the Big Bang, black holes. And that's why I think there has to be one unified theory that unites everything into the God equation.
Wow. So you don't think nature should be chaotic and messy and red and tooth and claw and just all over the place?
That's right. In fact, I first heard about this idea when I was 8 years old. When I was 8 years old, a great scientist had just died, and all the newspapers published a picture of his desk, just his desk, and the caption said, "This is the unfinished manuscript of the greatest scientist of our time." Well, I was hooked. I had to know, why couldn't he finish that? He could ask his mother, right? It's a homework problem. So I went to the library, and I had to know what was behind this. I found out the man's name was Albert Einstein, and that book was to be his crowning achievement. He wanted an equation 1 inch long, perhaps, that would unify all the great forces in the universe, and he failed. For 30 years, he tried to do that, and he failed. Well, I was hooked. When I was in high school, by the way, I built an atom smasher. I went to my mom and I said, "Can I have permission to build an electron accelerator in the garage?" And my mom said, "Sure, why not?" So I assembled 400 pounds of transformer steel, 22 miles of copper wire, and I built an atom smasher in the garage. Of course, every time I turned it on, I blew out all the circuit breakers in the house. My poor mom would just shake her head and say, why couldn't I have a son who plays basketball? Maybe if I buy him a baseball. And for God's sake, why can't he find a nice Japanese girlfriend? Why does he have to build these machines in the garage?
So was this the beginning for you of this quest to find the 1-inch theory that describes everything, seeing this photo of Einstein's desk?
That's right. One photograph changed my life. And I said to myself, that's for me. This is the greatest challenge, the Holy Grail of science, to unify all the laws of the universe into a single framework. And today, we think we have it. It's not in its final form, but we call it string theory, and it's based on music. Now, let's go back to the Greeks, philosophers 2,000 years ago. Pythagoras thought that the world was not made out of atoms, but made out of music. He saw a lyre string one day, and he noticed that the longer the string, the lower the note. He went to a blacksmith shop and saw a sword. The longer the sword, the lower the note. And he said, aha, the mathematics of music, the mathematics of notes and resonances and chords, that is rich enough to explain the vast diversity of the universe. The universe is based on music. Well, of course, that theory never went anywhere. The Roman Empire fell apart. For 1,000 years, there was darkness and superstition. But finally, now we have a new theory on the block, string theory, which does believe that, yes, Pythagoras was onto something, that if I had a super microscope that I could peer into an electron, the electron would not be a dot at all. It would be a rubber band. And if you twang it, it would vibrate at a different frequency. So an electron is one frequency, like this. A neutrino would be like this. A quark would be like this. They're nothing but different musical notes on the same string. So physics is the harmonies you can write on these vibrating strings. Chemistry is the melodies you can play when these strings bump into each other. The universe is a symphony of strings, and the mind of God that Albert Einstein chased after for so many decades, the mind of God is cosmic music resonating through hyperspace. That is the mind of God.
Let me make sure that I understand the basic idea of string theory. So we use your super microscope idea. We peer into the heart of the atom, and we peer into the subatomic particles that make up the atom. And instead of a hard ball, a particle in the middle, what we see is a little vibrating filament, one-dimensional string of energy.
My God, she's got it.
Loop, right? Okay.
You got it.
And okay, and then so each of these strings is vibrating at a particular frequency.
That's right.
And that makes it a certain thing. It determines its mass, its charge. What is it determining?
Yeah, like for example, we know that we have musical notes, A, B flat, C sharp. And these are just nothing but notes on the same string. The same piano string can give you A, B flat, C sharp, so on and so forth. And so from a distance, this rubber band looks like a dot, looks like a point particle. And so these particles can be then categorized by its quantum numbers, its harmonic frequencies, its mass, and so on and so forth. And then with this zoo of subatomic particles that we have, hundreds of subatomic particles when we smash protons, is nothing but musical notes coming from vibrating strings.
Okay, so the string, instead of giving us B flat, it gives us the electron.
That's right.
Okay, and then from these we build up to atoms, and then to molecules, and then to all of the stuff of the universe.
To the universe.
Trees, earth, air, all of these things.
So the universe is a symphony of these vibrating strings. And you see, therefore, that a very simple paradigm, music, is rich enough, as Pythagoras thought 2,000 years ago, to explain the diversity of nature. You see, atoms are great. We know that, of course, atoms do exist, but how many kinds of atoms are there? And how many subatomic particles out there? What is the rhyme or reason? What is the paradigm that unifies all the notes that you can, all the elements that you can write from atoms and all the subatomic particles? Again, Pythagoras said the only paradigm rich enough, simple, but rich enough to explain the diversity of matter is music, and the music of vibrating strings.
And so one of these vibrating strings would be the graviton, right?
That's right.
So
In fact, it's the lowest octave. The lowest octave of the string contains the graviton, a particle of gravity. In fact, if Einstein had never been born, we would have discovered all of general relativity as nothing but the lowest octave of a vibrating string. There it is. All of Einstein's theory has nothing but the lowest notes on a vibrating string. This is amazing.
The idea is that the graviton is one kind of vibrating string, the way the electron and the proton, everything else is a kind of vibrating string. And this is what unites all of the fundamental forces. They all come down to the same component part, which is the vibrating string.
That's right.
String theory unites gravity and space-time with everything else.
Right. And the standard model with scores of subatomic particles, gravity, they're nothing but the lowest octave. And the theory predicts higher octaves as well, beyond the musical octaves that we see around us. Everything you see around you is the lowest octave of the string, but they're higher octaves. And 2 weeks ago at Fermilab outside Chicago, big news. Mm-hmm. It turns out that the standard model of subatomic particles is very clumsy, very ugly, but it works. It does describe the quarks and the neutrinos. Nobody thinks it's the final theory. It's simply too ugly. It's a theory that, quote, only a mother can love, unquote. And now we suspect that the crack found just 2 weeks ago, the mu meson has a magnetic moment different from the theory, meaning that there's other particles, other resonances perhaps. And that's why string theorists are very excited. Is this the clue? The first clue in 50 years. In 50 years, we have seen no deviation from the standard model, the theory of almost everything, except finally we found a crack. A new particle perhaps will emerge, and we think that could be the next octave of the vibrating string.
Yeah, okay, let me explain to people a little bit about what we mean about new particles. So the standard model sort of has, the way the chemistry has a periodic table of the elements, the standard model of physics has a chart that lists all of the known particles and their properties, right? That's the standard model.
That's right.
The idea is, might there be something else we don't know about that's out in the universe? Might there be something that would kind of break the standard model and give us new physics, right?
Right, exactly. You see, we physicists believe that at the fundamental level, nature should be simple, elegant, beautiful. But the standard model is ugly, clumsy, contrived. It's sort of like taking an aardvark, a platypus, and a whale, scotch taping them together with scotch tape, and calling that nature's finest evolutionary creation, the end product of millions of years of evolution on the planet Earth. Nobody, even the creators of the standard model, realize that it's only a halfway house. But it works. It seems to work at low energies. Now at high energies, it seems to be breaking down. And you see, that's what's causing all the excitement. We need a clue. We need a clue that there's another theory out there that is beautiful, elegant, simple, because beauty is, believe it or not, one of the main drivers of physics. Physics shows that at the fundamental level, the laws of nature are simpler than we thought and more beautiful and gorgeous than we thought. So why should the ultimate theory be the ugliest theory known to science?
I always like that idea that in physics, and I think in math, elegance and simplicity is the most beautiful thing that you can have.
That's right. But the standard model has 36 quarks and antiquarks, 3 identical generations of particles, and 20 free parameters. You can't think of a theory more ugly than that, but it works at low energies. But at high energies, we think it fails. And a new theory is emerging right before our eyes. It could be string theory, or who knows, we'll wait and see. But this is big news.
Yeah, you don't talk about this experiment in your book, but you mentioned the idea that looking for a new particle is a little bit like the way that early astronomers looked for new planets, right?
Exactly.
So the idea was they knew where some planets were, but not the others. Mm-hmm. And they could infer that there must be something else out there because something was tugging on the orbit of the planets that they knew about, right?
Right.
And the same thing is going on with the muons that they're studying at Fermilab. The muon is moving in a way that's a little bit unexpected.
That's right. Well, as Einstein said, when you see the tail of a lion, you have to assume that there could be a lion at the other end, and this could be the tail of the lion. And remember, there's now something called dark matter that astronomers have discovered. Dark matter surrounds the galaxy. It's invisible, holds the galaxy together. We don't know what it is. It could be the next octave of the string. I tell young students, people who are listening to this program, for example, that if you ever find out what dark matter is, the first thing you should do is tell me first. And we'll split the Nobel Prize money together. You and me will split the Nobel Prize, because that's what it's worth. A new form of matter out there, more plentiful than ordinary matter, called dark matter, invisible matter. And we think it could be the next octave up of the string.
Okay, so this, whatever it is that's making the muon move, wobble more than it should, you think maybe that might give us some clues about dark matter.
Exactly. The mu1 is a partner of the electron. It weighs more, about 200 times more than the electron, but otherwise it's identical to the electron. And we now find out that its magnetic properties differ from the theory. The standard model says the magnetic properties should be like this, but it's actually measured to be something different. Mm-hmm. So that's a deviation. The first deviation in 50 years, I should point out. For 50 years, we've been stuck. We've been stuck with the theory of almost everything, the standard model, because it works. But now we have the first clue that there could be new physics, a new force, perhaps the next octave of a vibrating string.
Okay, so let's talk. So we talked a little bit about dark matter. What other physics or cosmology questions does string theory help us examine?
Well, children, when they hear about the Big Bang, they say, Mommy, Daddy, what is the universe expanding into? Mm-hmm. And at that point, Mommy and Daddy say, ask your teacher, right? Well, Einstein gives us a picture that the universe is a bubble of some sort. We live on the skin of the bubble, and the bubble is expanding. That's called the Big Bang theory. String theory says that if it's a quantum theory, there's a certain finite probability that there are other bubbles out there, other bubbles. And when these bubbles collide, that's the Big Bang. Or the bubble fissions in half. That is what the Big Bang is. This is the multiverse idea. It replaces the single bubble with a bubble bath of parallel universes. And then I know the next question that I always get whenever I talk about parallel universes is Elvis Presley still alive in a parallel universe?
And
well, yeah. There's a certain finite probability that there's a universe out there where Elvis Presley is still belting out those hit after hit in another universe. Not in our universe. In our universe, unfortunately, he passed away.
So let me make sure I understand. You're talking about this idea that people call the space-time foam, right?
Exactly.
There is no real vacuum of space. There is nothing.
Exactly. That's right. If I had a super duper microscope, it can see the fabric of space-time. Einstein thought it was curved. But now, even if you look even carefully at the curved space-time, it's bubbly. From a distance, it looks curved and like a trampoline net. But up close, there's little bubbles. Each bubble is a potential universe. They pop into existence and pop out of existence, so we never see them. It looks like the vacuum. But one day, one of these bubbles actually did not pop back. It just kept on going and going, and that is our universe. So we think our universe came from a parent universe. Now, we're going to launch a satellite in the future called LISA. It's a gravity wave detector in outer space. It'll give us the first baby pictures of the infant universe as it emerges from the womb of the Big Bang. And maybe, just maybe, it'll pick evidence of an umbilical cord connecting our infant universe in the womb to a mother universe. Maybe that's where our universe came from. And one of the predictions of string theory is the multiverse of universes. Universes split off baby universes. In fact, that's what Stephen Hawking called them, baby universes. That's his nomenclature.
So in this idea, all of the bubble universes are independent. They're separate. What way then could they connect so that one universe could give rise to another?
Well, we don't know, but we think that quantum mechanics says that there's a certain probability that if you have a soap bubble, the soap bubble could fission in half. Now, let's take a look at our universe. What is the net charge, electrical charge of our universe? Positive cancels negative. We learned that in high school. Therefore, the net charge of the universe is 0. What is the net spin of the universe? Well, galaxies point in all directions. They average out to 0. What is the matter energy content of the universe? Gravity has negative energy. Ordinary matter has positive energy. They add up to give you 0. In other words, our universe is compatible with 0. 0 charge, 0 spin, 0 matter energy. In other words, our universe came from nothing. Our universe was a quantum fluctuation of a parent universe, which also had the quantum numbers of nothing. And remember, the Bible refers to the mist. Well, perhaps that's where our universe came from. It came from nothing. A quantum fluctuation out of the quantum foam. One bubble decided to keep on going, and that became our universe.
So all of these little tiny universes popping in and out of existence, ours just takes off. It gets really big. And
That's
it
right.
lasts almost 14 billion years so far, right?
That's right. In other words, universes are being born even as we talk. Even as we talked, universes somewhere far, far away have been exploding, giving you other big bangs throughout the multiverse. And again, this is the dominant picture coming from experimental data. Inflation fits all the experimental data. And inflation says that if the universe was born as a quantum event, it can happen again and again, because there's a probability that it could happen again and again and again. So we're naturally led to the multiverse idea by looking at quantum mechanics.
So let me ask you, when we study the formation of planets and the search for life in space, we have this idea of the Goldilocks zone for a planet. That is not too close to its sun and it's not too far from its sun so that it can support liquid water and therefore life as we know it. So we have this idea of the Goldilocks habitable zone for a planet. Do we have that idea for universes? That there's something that would make the perfect conditions for a universe to be stable and to last as long as our universe has?
Exactly. This is called the anthropic principle. You see, if the nuclear force were a little bit stronger, the sun would have burnt out billions of years ago and we wouldn't be here. If the nuclear force were weaker, then the sun would never ignite it to begin with, and we still wouldn't be here. If gravity were a bit stronger, the universe would have exploded and freeze to death, and we'd all be frozen in a big freeze. If gravity were a little bit stronger, the universe would expand it and contract it to a big crunch, and we still wouldn't be here. Now, there are many accidents. The universe is just right to make 4 intelligent beings. Okay? And so what does that mean? Well, maybe there are other universes out there where the nuclear force is too weak, is too strong. Stars never ignite, or they burn out, and therefore there's no life on these universes. In other words, congratulations, we hit the jackpot. We happen to be on a planet that is just right from the sun, and a planet that's just right to have stars that ignite and gravity that doesn't freeze us to death.
Wow. So let me ask you, that's one of the very mind-bending ideas in string theory. Let me ask you about another one that I have always found very hard to understand. So string theory only works if there are 10 or 11 dimensions.
That's right.
And now we're used to 3 spatial dimensions plus time. What are these other 6, and where are these other 6?
Well, there are 4 fundamental forces, and if you try to write the equations for these 4 and put them together, they don't fit. Now, when you start to go to a higher dimension, then the forces begin to fit mathematically together. And when you go to 10 dimensions, 11, there's enough room. There's enough room to fit all the fundamental forces together. And so we don't like it. We would prefer to be in a 3-dimensional universe, but the math says, no. In lower dimensions, string theories are inconsistent. They have what are called anomalies. In other words, 2 plus 2 equals 5, you can prove in some of these other universes. Now, of course, 2 plus 2 is 4. So we want a universe which is mathematically consistent. The only mathematically consistent universes are in 10 and 11 dimensions. Why? Well, I don't know. It's just the math. That's where the math takes us, okay? Now, some people think, well, that's too fantastic. I mean, who can believe in hyperspace? This is something out of Star Trek. Well, get used to it. That's the way the theory seems to go. Again, we need proof. And that's where LISA comes in, measuring the instant of the Big Bang. That's where dark matter experiments come in, trying to find dark matter in the laboratory as a higher octave of the string. And then the Fermilab experiment of 2 weeks ago. All of them point to the fact that it is measurable. There are measurements we can make to prove or disprove this theory. This theory is testable. It is reproducible, and it is falsifiable. That qualifies for it to be a science, even though at the present time, we have no direct proof.
I was just going to ask you, so this is one of the big criticisms of string theory, is that you can't really test it in a lab. There's not
directly.
Yeah.
Indirect tests are possible. Now think of the sun. How do we know that the sun is made out of hydrogen? We've never been there, God forbid. We know that the sun is made out of hydrogen because of indirect measurements, echoes from the sun called sunlight. That's how we know that the sun is made out of hydrogen. That's how we know what the stars are made out of. We want to have echoes from the 10th dimension. The 10th dimension gives you predictions, echoes that reverberate in 3 dimensions, and that's how we will test this theory.
Okay, so give us an example. What might be an echo of this, the 10th dimension that we could test, that we could observe?
Well, one thing you can do even in your living room is to test the inverse square law of Isaac Newton. When you're in high school, you learn that the farther you are away from the Earth, the weaker the gravity. It drops as the inverse square. Why square? Why not cube? Why not quartic? Why not quintic? It's square. That's because space is 3-dimensional, and spheres in 3 dimensions are defined in 2 dimensions. A sphere is 2-dimensional. That's how we know that gravity diminishes the inverse square. So we've never really measured gravity in your living room. We've measured gravity for Saturn, for Jupiter, for stars, for galaxies. Newton's laws, the inverse square law, works fine for outer space, but we've never done it in your living room. That's what we're doing now. We're now doing experiments in the laboratory to look for deviations from the inverse square law, which would signal the presence of a higher dimension that we cannot see, but is there.
Can you tell us a little bit more about the LISA project and what that might tell us?
Exactly. There's a new kind of telescope called gravity wave detectors. You know, optical telescopes opened up the universe. Galileo showed how to do that. Then after World War II, radio telescopes became popular, and that opened up the world to quasars and now black holes. Now we want gravity wave detectors, which won the Nobel Prize recently to several physicists who built 2 of them, one in Louisiana and one in Washington State. Now we want to put them in outer space. LISA consists of 3 satellites separated by laser beams 3 million miles across.
Wow.
This is the largest machine of science ever conceived of by the human mind. It'll pick up vibrations from the instant of the Big Bang. Now, believe it or not, when you turn on a radio and you get static, some of that static comes from the Big Bang. This is amazing. You're actually listening to the creation of the universe when your radio is tuned between frequencies. Now, with this gigantic LISA, we're going to get baby pictures of the infant universe. Now, you see pictures of the microwave background radiation. That's a picture 300,000 years after the Big Bang, when the universe is like a young boy or young girl. No, we want the universe as it's being born, a trillionth of a second after creation. That's what we want. And that's what we're going to get, we hope, with LISA, and maybe even indications of the pre-Big Bang universe. The radiation from the Big Bang can now be tested against string theory. String theory goes backwards in time before the Big Bang. You can run the videotape backwards on string theory, and you can then test Test to see which string theory is correct by running the videotape backwards before creation. This is amazing. The first time in history that we might be able to get an inkling of the pre-Big Bang universe.
And so that's been particularly hard to study. We can model the moment of the Big Bang, and we can model the 13.8 billion years after that, but the moment of the bang and right before is very, very hard, right?
Right, that's called the Planck energy. The Planck energy is 10 to the 19 billion electron volts. It is the energy of the bang itself, and that's where string theory lives. String theory really lives at the Planck energy. That's when all the symmetries are unbroken. It's pure crystallized symmetry. That's the Planck energy, the energy of the Big Bang itself. And string theory even takes you before creation itself. And so if the universe came out of a parent universe, or the collision of two universes, we should be able to detect the radiation from that with LISA, hopefully keeping our fingers crossed if the satellite goes up into orbit.
Okay, so there's the projects like LISA, then there's the project like what we spoke of at Fermilab with trying to figure out if there might be new subatomic particles we don't know about. Fermilab relies on, a bigger particle accelerator than the one you built in the garage.
That's right.
Do you think the solution is we have to build ever bigger particle accelerators and that's what we need?
Well, that would be nice, not necessary. The Japanese, the Chinese, and the European Union have now put proposals for a super duper machine, even bigger than the Large Hadron Collider. My machine was 2 million electron volts. We're talking about a machine now, maybe up to 20 trillion electron volts, being proposed by the Japanese, the Chinese, and the Europeans. And so this is amazing that we may have direct proof of these theories by creating a new generation of subatomic particles. Another way to prove it is pure mathematics. String theory is well defined mathematically. No one is smart enough to solve it. That's right. Nobody on Earth is smart enough to solve all these equations. We have the equations. We're just not smart enough to solve them all. Once we do, we should be able to calculate the mass of the proton from first principles. That's the name of the game. The subatomic particles that we see and love, the electron, the proton, the neutrino, we should be able to calculate their properties from first principles. If we do that, game over. Well, because it means that we can extrapolate the high energies, but if we can explain the low energy world that you and me see all around us from first principles, that's it.
But if we're not smart enough to do it, then who does it?
Well, maybe some young person watching this program and listening to your words will be inspired like I was when I was 8 years old. The theory exists. It's just not in final form. We now have membranes that coexist with strings, and membranes are much more difficult to work with. I'm working on membranes right now myself. Very difficult, but once we get the complete theory, then that should be it. I like to think of it as a young boy walking in the sands of Egypt, bumping into a pebble, and then the boy brushes away the sand and finds out that it's the top of a pyramid. And excavation starts. You find hieroglyphics, strange diagrams, strange blueprints, and after decades of brushing away the sand, we're now at the ground floor. And we're just about to open the pyramid to find out who built the pyramid, how is the pyramid built. That's where we are today. That's how complex this theory is. It was discovered by accident. We were not supposed to see this theory, perhaps in this century. By accident, we discovered this theory by thumbing through a math book, for God's sake. And that's why we're discovering that it is smarter than we are. The theory has shocked the world of mathematics. Mathematicians are trying to learn this theory. The Nobel Prize of Math is called the Fields Medal. Fields medalists are trying to learn this theory. That's how advanced this theory is. But like I said, we're on the ground floor, and I think one day we will open the door and see all the predictions, good or bad, of this theory.
All right, so string theory is not finished yet.
No, and somebody could finish it listening to this program. It's up for grabs. You don't have to be rich. You don't have to be famous. No, you could be just a recluse working in your desk and solve the theory completely. Now, the equation that you have to solve, part of it is my equation. I'm the co-founder of string field theory, which allows you to summarize string theory into an equation about this long. That's my equation. I reprinted it in the book. But now we have membranes. So we have to enlarge that equation a bit. But we think, pardon?
Oh, sorry, I was just going to say, explain what a membrane is for people who don't know.
Well, a membrane is like a beach ball or a sphere. It's a round object. And if I squeeze this beach ball, it becomes a string. So strings emerge naturally in the limits of a beach ball. So a membrane is like a drum head, it's like a beach ball, but it's much more complicated than a string. Strings are relatively easy to work with. Membranes are more difficult. So we think in fact, we think our universe, we think, is a membrane.
Whoa, wait a minute. Say that again. What does it mean that our universe is a membrane?
Well, subatomic particles, we think, are nothing but notes on a vibrating string. But strings also coexist with membranes, we now know. And one membrane could be the entire universe. So in other words, the entire universe emerges as a solution of string theory.
Wow.
In other words, if Einstein had never been born and we never discovered the quark model and the standard model, all of it would have come out of string theory anyway. It's self-contained. It's hidden right there in the lowest notes of the string.
Is that a way of saying that the mathematical principles that all of this follows, it exists independent of the universe, that it precedes the universe in a way?
If you're a Platonist, in some sense, yes. Plato wondered whether or not there was a higher plane of existence where, like pure mathematics could exist. String theory is pure mathematics. It has no adjustable parameters. It either is everything or it's nothing. It's totally self-contained, mathematically consistent, and for free, it gives you all of Einstein's theory and the standard model. Now, the other criticism of string theory, to be honest, is that it does predict other universes. Now, think for a moment of Newton's equations. How many solutions of Newton's equations are there? An infinite number. You have one equation for a marble, another for a cannonball, another for a rocket ship. You have to tell me what you're starting with, and then Newton's laws will tell you how the rocket ship, how the marble moves. String theory is a theory of universes. Therefore, it has an infinite number of solutions, just like marbles and spaceships. But you have to tell me. You have to tell me what you're starting with, and that we don't know. We don't know the initial conditions at the Planck energy, the instant of the Big Bang. If we did know, then of course we could test it immediately. But we don't know the initial conditions of the universe. That's an experimental problem. And so yes, string theory does predict other universes. But so does Newton's laws. How do you tell which one is correct? You have to tell me what you're talking about, whether it's a marble, a spaceship, a planet, the stars. You tell me that you're working with marbles, and I can give you the solution. Same thing with string theory. We don't know the initial conditions of the instant of creation. Sorry about that. Once we figure that out, LISA, by the way, LISA may give us an inkling, because LISA will be the first telescope to appear within a trillionth of a second of the Big Bang. Not 300,000 years after the bang, but almost at the instant of the bang. That's where LISA will take us.
So string theory proposes a multiverse, but these, at the moment, they're mathematical possibilities. We don't know if these other universes exist. Is that right?
That's right. We don't know whether these other universes exist. We live in a universe where life is possible. That's called the anthropic principle. But there's another principle, too, called the Copernican principle. The Copernican principle says there's nothing special about the Earth. There's nothing special about our universe. Our universe is very ordinary. The Earth is very ordinary. Our place in the universe is very ordinary. That's the Copernican principle. And in fact, Douglas Adams, the comic science fiction writer, once had a machine that would drive any sane person insane. It's the insanity machine. You enter the machine, and there's a picture of the entire universe with an arrow. The arrow says, "You are here."
Yes.
and that drives any human mad, berserk. Well, that's the Copernican principle. You are here in a map of the universe. The anthropic principle says the opposite. The anthropic principle says our universe is special. It has life, conscious life. It has stable matter, beings that think, that have self-awareness. We're special. And both theories are compatible with the known laws of physics. They're total opposites, but they are both compatible with the known laws of physics.
I remember that Douglas Adams. I think it's called the total perspective vortex. That's the machine that drives everybody crazy.
That drives you insane.
Well, before I see questions are starting to come in. So let me just ask you a couple of sort of the big philosophical questions
Sure.
you address at the end of the book, and then we'll take some questions from the viewers. So one is, I want to know, right in the title, when you say the God equation, who or what do you mean by God?
Well, Einstein coined the term. First of all, Einstein did not believe in a personal God that smites the Philistines, gives you that bicycle for Christmas that you wanted. He didn't believe in a personal God. He believed in a God of order, simplicity, harmony, beauty. The universe could have been ugly. It could have been chaotic. It could have been random. It could have been just a bunch of electrons and neutrinos, a mist of nothingness. But here we are. The universe is gorgeous. On a sheet of paper, you can write down the theory of almost everything. It's not very pretty, but still on a sheet of paper, you can write down relativity and the standard model. It didn't have to be that way. So Einstein thought of himself as a young boy entering a library, this huge library of the universe. And all he could do was open the first book, first page, first chapter. That's where we are today. Now, Galileo had a slightly different point of view. Galileo said that the purpose of science is to determine how the heavens go. The purpose of religion is to determine how to go to heaven. So, in other words, science is about natural law, how the heavens go. But religion is about ethics, how to go to heaven, how to become an upstanding citizen, how to love your neighbor. And they're compatible. There's no contradiction between them as long as you keep them separate. The problem occurs when people who are in the sciences pontificate about ethics and religion, and people who are religious begin to pontificate about natural law. That's where we get into trouble. But as long as we keep these two spheres separate but complementary, there's no problem at all.
So you had a very interesting idea you write towards the end of the book about being raised by Buddhist parents, but also being raised in the Presbyterian faith. And these are two groups that have very different ideas about how the universe begins and ends. In the Christian faith, there's a definite moment of creation and a definite moment of revelation, the end. In the Buddhist faith, there's an eternal nirvana. You have an idea about how string theory and might reconcile the two. So what's your idea?
So either the universe had a beginning or it didn't. There's no two ways around it until now. You see, our universe, our bubble, had a beginning, the Big Bang. We have tons of experimental data proving that fact. But our bubble universe coexists with other bubbles out there. And this multiverse, in what universe is the multiverse? Does it exist? It exists in a higher dimension. Our bubble is a three-dimensional bubble, but it coexists with other bubbles floating in 10 or 11-dimensional hyperspace. So what is nirvana? Nirvana is 11-dimensional hyperspace. That is the arena in which the bubbles float and can bump into each other. And so the two pictures are complementary. A multiverse of universe is consistent with all the mathematical data, and this inflationary theory agrees with all the experimental numbers that we've seen so far about the Big Bang. And the inflation theory is a quantum theory, meaning that there's a probability it could happen again and again and again.
Wow. So our universe has an end, but the multiverse goes on.
That's right. Yeah. That's right.
So the way that our universe ends, there are conflicting theories, but none of them are good for us, right?
The second law is a death warrant. The second law of thermodynamics says that in a closed system, everything must die. Everything decays, rots, falls apart. Everything must die in a closed system. However, the key word is closed. If our universe is open, then it's possible to defy the end of the universe. So trillions of years from now, the universe will consist of dead black holes, dead neutron stars, dead matter everywhere. No stars, nothing illuminating, no life possible. At that point, trillions of years from now, I think we'll be smart enough to use this theory to build a lifeboat. a dimensional subway car, to leave our universe, to enter a warmer, younger universe, and we could mess up that universe as well. We'll have two universes to mess up then. So the end of the universe does not mean the end of life. Life can transcend the end of everything by leaving everything and going into another place.
And the way we get there is a wormhole, right? You have to be willing to go through a wormhole.
That's right. In 1935, Einstein himself introduced the concept of a wormhole. What is a wormhole? If you read Alice in Wonderland, the looking glass is the wormhole. It is a gateway connecting Oxford with the countryside of Wonderland. And it is a solution of Einstein's equations. Stephen Hawking thought they really were possible. Now, using wormhole for a time machine, he had some doubts, but he said, yes, wormholes seem to be compatible with the laws of physics, and maybe there's a white hole at the other end of a black hole. And some people say, if that's true, maybe our universe is a white hole.
Wow. All right. Last question from me before we switch it over to some audience questions. But if a wormhole materializes in your backyard and there's a possibility of going through it to another universe, would you go?
I would volunteer to be the second person to go through that wormhole. I think it'd be too dangerous to be the first person to go through. Now, what's the problem? The problem is graviton radiation. As you pointed out, a graviton is a particle of gravity. And if you calculate the graviton radiation of a wormhole, it's enough to blow up and explode the time machine or wormhole machine. But that's using ordinary Einstein theory. If you use string theory, then perhaps these quantum corrections are finite, because in string theory, everything is finite. There's no divergences at all. Then it's possible to go through the wormhole to perhaps another universe. You can't rule that out, but like I said, I'm no astronaut. I'm not going to be the one to have my name in lights. I'd rather just sit back and with pencil and paper and work out the consequences.
All right, that's perfect. Are you ready for some questions from the
sure.
audience? Okay,
fire away.
All right. So question one, this is a very good question. Somebody wants to understand, what exactly is the string made of?
Well, the string is, we think, the ultimate substance out of which everything else can be made. So when you think of atoms, people ask the question, what is the atom made of? You see, the question has no meaning because everything is made out of atoms. Well, now we think the atoms are made out of strings, and we have the same question. What is the strings made out of? The closest you can say is that strings are condensed energy. Think of energy that condenses into the form of a string in the same way that magnetism also condenses to create magnetic lines of force. We think that a string is basically pure energy condensed into a vibrating string.
All right, good. Well, we have a couple of Einstein-related questions. So the first one is, if you had the opportunity to ask Einstein a question, what would it be?
Well, I would try to ask him, what would he think about this? Because you see, string theory not only goes beyond Einstein, it's also a quantum theory. And Einstein, of course, had qualms about the quantum theory. Einstein's philosophy was there's a deeper theory. Not that the quantum theory was wrong, but that it was a deeper theory underlying the quantum theory that was deterministic. But for all we can tell, the universe is not deterministic. We have an uncertainty principle, and the uncertainty principle guides all of our work with lasers, with transistors, the internet, computers. They're all based on the uncertainty principle. So I would ask Einstein, what's your opinion about string theory? Given the fact that it contains your theory, all of your theory has nothing but the lowest vibration, but it is a quantum theory. Sorry about that, Albert.
Somebody else wants to know, other than Einstein, who are some of your other science heroes?
Well, if you were to rank the greatest minds of science, I think number one would be Isaac Newton, because from scratch, from witchcraft, sorcery, magic, he writes down calculus and the laws of motion. Einstein then uses the calculus of Newton. He uses vector calculus, tensor calculus, to write down the equations of relativity. And then Darwin. Darwin had the nerve to go up against thousands of years of religious lore about natural law to say that, well, evolution is a principle, a scientific concept that can explain the vast diversity of life on the planet Earth. So I think Darwin would be right up there because he was the one who gave us the great paradigm of evolution, which then explains the diversity of life in the universe.
We have a question that it's a really good one about the Fermilab news that we were talking about before about the muon. So the question is, has a new particle been fully verified, or could it all be measurement errors?
Well, everything is measurement error as a possibility. Physics depends on things that are testable, reproducible, and falsifiable. These are the three criterion for science. So this theory has to be reproduced again. That's just the name of the game. In fact, during World War II, before World War II, the Nazis wrote a book denouncing Einstein, and the book was entitled 100 Authorities Against Einstein. And Einstein was shown the book by the Nazis, and he was asked a comment, 100 great German scientists against Einstein. And Einstein said, you don't need 100 authorities. You just need one experimental fact to disprove relativity. And the same thing with this muon result. This is fantastic if it's true. The first time in 50 years that we have a crack in the standard model, but one experiment that shows it's false can negate the whole theory. It has to be reproduced. But if it holds up, it's big news. It means that for 50 years, we've been chasing the tail of a lion, not the lion itself.
Well, tell me if I'm understanding this correctly, but my understanding is that these equations for predicting what the muon should be doing have a lot of variables in them. And not everybody agrees on the values of some of the variables. So the very day that study came out, another study came out that said, actually, you should be using a different value for one of the variables. Maybe it is just a math error.
Yeah, that's why science is based on things that are testable and reproducible. And that's why physicists are saying that at the present time, if it holds up, that's the key word, if it holds up, this is big news. But remember, a few years ago, there was a report coming out of Geneva, Switzerland, saying that neutrinos go faster than the speed of light. So Einstein was wrong. Sorry about that, Albert. Your theory was wrong. Well, they found out that they miscalibrated the distance between Switzerland and Italy, and that distance was calibrated using the GPS system. The GPS system uses Einstein's theory of relativity. So they were using Einstein to disprove Einstein. Well, anyway, sure enough, people found out they miscalibrated the GPS. They miscalibrated the distance between Geneva and Italy, and bingo, you do the calculation correctly, and once again, Einstein wins. Well, the standard model has to be proven. And it has to be tested. Every single challenge has to be met. And that's why we want to retest this experiment again and again to make sure that we're onto something really hot.
Okay, here's a good question. Somebody asked, why is it so difficult to describe the 7 dimensions beyond the 3 spatial dimensions plus time? How can we even conceive of these?
The reason is evolution. You see, your PC has no problems calculating in n-dimensional hyperspace, inverse matrices that are n-dimensional all the time. However, the problem is evolution. We evolved to evolve 3-dimensional tigers, 3-dimensional lions. A 10-dimensional lion never tried to attack us. Therefore, our brain never had to evolve to accommodate the motion in higher dimensions. However, when we physicists work in higher dimensions, how do we do it? We take slices of our universe, and that's how we visualize higher dimensions. Now, artists have been fascinated by this. Salvador Dali, many of his famous paintings are based on the 4th spatial dimension. His famous painting of Jesus Christ is called Hypercubicus Crucifixion. Jesus Christ crucified in the 4th spatial dimension. He's crucified on a tesseract. A tesseract is an unraveled 4-dimensional hypercube. And when Salvador Dali painted melted clocks, he was trying to represent time as the 4th dimension by having clocks that were melted. So you see, Salvador Dali would spend time at the math department at Brown University pumping information from the mathematicians, trying to visualize higher dimensions on a canvas. And that became surrealism.
Wow. So Sometimes people say these other dimensions are curled up. I'm not sure what that means. What does it mean? Does it mean they're very tiny? What does a curled up dimension mean?
Well, let's say, for example, that your living room is curled up so that you go to the left, and all of a sudden you appear to the right. Now, of course, that's not going to happen. But if our universe was curled up, you go to the left, and then instantly you materialize to the right. So your universe is a circle. If your universe is a circle and you move to the left, you emerge to the right. Now, where do you see that? You see that in the computer games. In computer games, your rocket ship disappears to the left, and where does it emerge? It emerges on the right, okay? What is that called? That's called a circle. Now, if you move this way and you wind up in this direction, or you go this way and you wind up in that direction in 2 dimensions, what is that called? A donut. That is the topology of a donut. You move this way, you wind up over here. That's going around the donut. Or you can go around the donut this way. And so we think that our universe could be a hypersphere, so that if you go, in other words, if you had a telescope and could see the farthest object in the universe is the back of your head. You would see the back of your head and say, oh, I didn't comb my hair today. I should have combed my hair. That's what the telescope just picked up. Now, we don't know. We don't know if our universe is infinite or finite, whether it's a donut, a sphere. But Einstein says it's a bubble of some sort. Maybe infinitely big, maybe small. But that's how we visualize these higher dimensions, by wrapping them up. So why can't we enter the 10th dimension? Well, because it's at the beginning of time, it was big, but it curled up. And so it's so small, you can't move in the 10th dimension anymore.
So we're too big for the 10th dimension.
Yeah, we're too big for these other dimensions, right? But a long time ago, if you move to the left, you emerge from the right. The universe could have been a sphere, except that sphere got smaller and smaller and then began to collapse.
That's absolutely wild. And the idea is we would not sense these dimensions. We don't have a sensory apparatus for them because we didn't need to. There was no evolutionary reason.
Exactly. And remember, there's nothing special about the number 3. In mathematics, 3 is a very ordinary number. There are so-called magic numbers of mathematics, by the way, and 10 and 11 of the string actually are some of the magic numbers. So string theory actually does incorporate the magic numbers of mathematics, but 3 is not one of them. There's nothing special about the number 3 as far as we can tell.
Let me ask you this one, a little bit of a different topic. Somebody asks, is it hubris for humans to believe that we're truly alone in the universe?
I think so. First of all, I like to think that with the equations that I write down, somebody on the other end of the galaxy is writing down the same equations, but in a different notation, because these equations are universal. You know, if you read Shakespeare, it's great, fantastic, but Shakespeare can only be appreciated if you understand English. But physics is universal throughout the entire universe. So I think the aliens are out there. There are 4,000 planets that we've discovered so far. And I'm on the internet. A lot of people email me and they say to me, Professor, you're wrong. You're wrong. The aliens are not there. The aliens are here. How do you know they're here? Because I visited them. They say they've been kidnapped by flying saucer people. Well, I have a word of advice. The next time you are kidnapped by a flying saucer, for God's sake, steal something. An alien chip, an alien paperclip, an alien calculator, anything. There's no law. There's no law against stealing from an extraterrestrial civilization. You're not going to go to jail. Who's going to put you in jail? And you'll have proof, living proof that these aliens do exist, rather than tall tales and hearsay.
I like the idea that aliens have paper clips. They have a lot of papers they gotta keep together. Wouldn't that be dangerous though? Don't we want to not advertise to the aliens that we're here?
I think it's a bad idea. I agree with the late Stephen Hawking, who said, well, remember what happened to Cortez when he met Montezuma? Montezuma made one of the biggest mistakes in history. He thought that Cortez was a god. Actually, Cortez was a pirate with steel, a written language, the horse, and gunpowder. The Aztecs had no horse. The Aztecs had no steel. They had bronze. They had no written language. And Cortez had smallpox. It was no contest. The Aztec civilization collapsed within a matter of months, meeting a small band of pirates from Spain. So I would hope that the aliens are peaceful, that they're not going to want to conquer us. But I look at it this way from the aliens' point of view. If you're going through a forest and you meet a squirrel, do you go down to the squirrel and talk to the squirrel? Well, at first you may want to chat with a squirrel, but then you get bored because the squirrel doesn't talk back to you and the squirrel has nothing interesting to say. Well, we are these people, we are the squirrels. And why should the aliens want to talk to us? Because we're rather boring. Do they want our gold? Gold is rather useless for them. What do they want that we have? Nothing really. Culture, mathematics, steel. We don't really have much that they want anyway. So they'll pretty much leave us alone, I think.
Well, I should just note for the audience, we have time for one or two last questions if anybody wants to put last questions through. I was going to ask you, if there are aliens, do you think we even exist in the same time with them? Do you think their civilization has already risen and fallen? I mean, space is really big, right?
Really big, but I think something even different. I think in the future, aliens will digitize themselves. We're already digitizing ourselves with the internet and stuff like that. We're going to digitize our personality and put our soul, our digitized soul, on a laser beam and shoot it through outer space at the speed of light. At the speed of light, we will conquer the universe. We will explore the universe without rockets, without accidents, without radiation, without weightlessness, as pure energy, digitized energy on laser beams scattered throughout the universe. And on the moon, there could be a mainframe that downloads your soul, your digitized soul on the moon. And there's an avatar that looks like you, is superhuman, super strong, super beautiful, super gorgeous, whatever, walking on the moon, colonizing the universe at the speed of light. That's how the aliens, I think, are going to explore the universe, not with rocket ships. I mean, that's so 60s technology.
It's going to be harder to steal from them in this scenario, though.
That's right. The aliens are going to be thousands of years ahead of us, and they're going to digitize themselves and send their digital signature to explore the universe at the speed of light. Think about that. In 100,000 years, they can explore the entire galaxy.
Wow. All right, let me ask you, we just had a question come through that I quite like. Somebody would like to know if you have any thoughts on quantum entanglement.
Well, if you're a fan of Star Trek, you have to communicate with Starfleet headquarters at the speed faster than the speed of light. So there's something called quantum entanglement that Einstein did not like at all. If I take two electrons and put them together, they vibrate in unison. But if I separate them, they still vibrate in unison, but there's an umbilical cord that shows up between these two strings. So if you vibrate one, then the other senses it faster than the speed of light. Now, Einstein hated that idea because he said nothing can go faster than the speed of light. But you see, we've tested it. Einstein was wrong. But Einstein has the last laugh because the information you send faster than the speed of light between these two electrons, that information is random information. It's chaotic. It's not Morse code. Morse code, you can send messages, I love you, whatever, on the internet. No, between the two electrons, there's an umbilical cord that has no information content. So Einstein has the last laugh. Yes, something went faster than the speed of light, but it's useless information. Sorry about that. You still cannot break the light barrier with usable information. Morse code cannot be sent this way.
Well, I think we are now out of questions. And I just wanted to say what a delight it has been to talk to you. This has been so fun.
Yes.
So let me just close by telling everybody, first of all, thank you, Dr. Kaku. He's the professor of theoretical physics at the City College of New York. And you can find his book, The God Equation, The Quest for a Theory of Everything, at your local bookstore. If you'd like to watch more virtual programs or learn more about the Commonwealth Club's efforts, you can go to commonwealthclub.org. Thank you so much, Dr. Kaku. It's been a delight. I'm Kara Platoni. And I'll see you next time.
Okay, thank you very much. Great honor.